Today we're going to continue our discussion on scatter plots, and specifically our scatter plots that end up having linear forms with no outliers. So we did talk and when we made scatter plots about how to describe them, whether they're linear or curved, if they're positive, negative, whether or not they have a strong, moderate, or weak, or even no relationship. No relationship would be a correlation of 0. And we could calculate correlation only if we had a linear relationship and if we had a scatter plot with no outliers. And so then we can even go further and we can write a linear regression, a line of best fit, a trend line, trying to think of other words, a linear model. That's the one I think we use the most. We can basically write an equation of a line that best represents the data set. It's not going to go through all the points. You might have experience with this already, but if you don't, when we get this linear model, we can graph a line into our scatter plot that fits the trend, that fits the data. That line's not going to go through all the data points because they're not in a straight line unless they have a correlation of +1 or -1, which we typically will not have in this class. The world doesn't work perfectly like that. And so in order to play along, I will explain what these numbers mean, but first get two lists. In list 1, put the age, in list 2, put the price, and then we can move forward. So here we have data on the age of Toyota Corollas that exist or are for sale within 250 miles of Redlands, California. Where Redlands, California is, I don't know. We could look it up if we want to. It's pretty specific. This is something you might do if you're searching for a car. You might want a search radius, a certain distance you're willing to travel to get the car. Obviously, you'd want to make that distance from your home and have a specific car you're looking for, and you can look at the age of cars and the price, and you might know that the older a car is, the less value it holds. And so let's make a scatter plot of this data. I've already done that, but you would go to your plot, choose the scatter plot one, make sure you chose the correct lists, and then we always zoom 9. And my equation's in there here. Let me turn it off. I'll actually clear it out. And so what you should get is something that looks linear. It looks pretty strong. I think we need to get comfortable with what strong and what moderate is. And it's negative. It goes down to the right. So our x-axis, our explanatory variable, that is the age of the car, and our response variable is the price, and that should make sense. The price sort of determines what the age sort of determines what the cost should be. And as a car gets older, as we go further to the right, the price decreases, the less you can sell it for. It doesn't look like we have any outliers here, so it is safe to calculate correlation. It's also safe to do linear regression and write a linear model for our relationship between age and price. And so we can do that by hitting stat, and we are going to calculate. And the same way we found the correlation, we're going to use option 8, linear regression. Tell it the appropriate lists, and we can calculate. So there again, we get our correlation. It should be negative, -0.9. Pretty strong, pretty close to -1. We'll talk about R squared another day. And then we get A and B. And if you look at the top here, you get y equals A plus bx. So it's giving you A, the constant, and B, the slope of a line that we could put into our calculator. So we could copy down A and B, and we could plug them in here, and we could write an equation, what we would call a linear model, to represent our data that would represent that line that was drawn through. But let me show you quick how we can get the line onto the graph pretty easily without having to take these numbers and long decimals and write them down. So if we go and stat calc again and choose linear regression as if we're just doing this all over again, if you go down to where it says store, it's going to store the regression equation. We're going to click the vars button. Don't click second first like we've been doing. Just click the vars button. And we want to go over to yvars. We want to store a function. And we want to tell it where to store the function. And we'll just store it in y1 since we shouldn't have any in there already. And so it's going to take the constant and the slope, and it's going to store those into y1, and then it's going to graph it for us like I had when I think I first popped up the scatter plot. And then again, it'll give us our output. And so then if we go look at the graph, my line is back there. And so if we want to go grab that equation, we can just hit the y equals button and the equation is in there for us. If you just want to grab it from the output when we do linear regression, that's totally fine too. But I'm going to grab this and I'm going to put it, I'm going to jot it down. So when I'm writing my model, I want to make sure that I'm using context. That's something we're going to do always. And so instead of using X's and Y's, I'm going to actually use the explanatory and response variable names. And so my explanatory variable was age. So instead of writing X, I'm going to write age. My response variable was price. So instead of writing Y, I'm going to write price. And one really big but looks maybe minor notation note is that for our response variable, we're going to put this little thing on here we call a hat, because we can use this linear model. This is a linear model. We can use it to make predictions for price of Toyota Corollas within 250 miles of Redlands, California, based on its age. And they will be just that, predictions. They won't be exact values. So much like our sample mean gets a bar on top because it's just from a sample, it's not for the entire population, our response variable when we're doing a linear model gets a hat so that we know we're not going to get an exact value here, we are going to get a prediction. And so often you'll be asked to describe what it means for the intercept. This is the y-intercept. And so that y-intercept is the cost of a 0-year-old vehicle. So that is when the age is 0. That's what our price will be. So a brand new Toyota Corolla is approximately $16,745.71. And that may or may not be the case, but that would be our prediction at 0. And of course, our slope means that as we add 1 year, to the age, we keep adding 1 year and adding 1 year. Each time we add 1 year, the price will go down $713.12. It's important to use the language that conveys that this is not an exact thing. So we could say on average. So our slope means that on average, as a car ages 1 year, it loses $713.12 of its value. Make sure we use the language on average. Somewhere in there that's conveying to somebody reading this that it's not guaranteed it's going to lose that amount of money, but on average, give or take, that's how much it will depreciate over a year. Oops. I also want to show you that sometimes you'll see these computer data outputs, and there's a lot of information in there, but what we can get is the intercept and the slope right here. This information that's circled is something we'll deal with later. Oh, and that's what it says. This is from the book. And so it will literally say intercept and give you a coefficient or a value. And then it'll name the explanatory variable. So in this case, it's protein. I think we're talking about burgers or something like that, and then the coefficient would be the slope, which again is pointed out here. So I just want you to see, because you might see these in the book or on a AP question, that you can find these values even if you don't have the data to put into your calculator. So I'm going to skip a couple of these pages. We're going to do them together, but what I do want to talk about is the relationship between the line and the actual data points. So obviously the data points on here actually represent Toyota Corollas in our data set, how much they cost, how old they are, and then this line is a linear model. All we're doing is modeling this relationship. We could also call it a prediction equation because we can use it to make predictions. We could predict approximate prices for Toyota Corollas based on our data set, but we would want to stay within the range of ages that we have. So I do believe that the oldest car we have is around 10 years old. So we can make predictions for the price of cars somewhere between 1 and 10 years old, maybe a little bit older than 10, but we wouldn't want to go too far. We wouldn't want to predict the price of a 30-year-old Toyota Corolla. It's too far away from our data set. So I just want to point out that we have this distance between our actual data point and the line. So this is the actual thing we observed. We would call it an observed. And then if we go straight up onto the line from that data point, this is what we would predict given our model. So this was a 1-year-old Toyota Corolla. The thing that we observed was the price that it was for sale. And that point on the linear model, the regression equation, the line, is what we would have predicted if we used our equation to calculate the cost of a 1-year-old Toyota Corolla. You can see they're not the same. There's some distance between those two things, and what we call that distance is a residual. It's the difference between what we would predict and what we would observe. And so we can calculate a residual that we call E, kind of for error, is observed minus predicted. And we're going to do a couple of these maybe together in class. And so data points below our linear model will always have a negative residual. The data points above our linear model will have a positive residual. Any data point that is on the line, exactly on the line, will have a residual of 0. That usually doesn't happen. We have some that are kind of close. I don't know if they're exact, and so their residual would be very small. The larger the residual, the more likely something is an outlier. So if you can calculate a residual that is very big, you may have missed an outlier. So again, we'll talk a little bit about making predictions and calculating residuals in class together. As always, please watch to the end. Please answer the questions. Please do ask questions if you have them. Take your time, and good luck.